Good morning, ladies and gentlemen. On behalf of Dublin City University and TechWorks Marine, I'm pleased to welcome you to this seminar, where we will give you an overview of the AWAMS project funded through Enterprise Ireland and the first Disruptive Technologies Innovation Call. So the third round has just been announced, so we're the first ones. A 3-year timeline project, of which we are halfway through at the moment. It is great to see the interest we've had on this project on a global scale, with people from countries as far away as Peru, Poland, India, Korea, Portugal, as well as Ireland, closer to home here. And within that mix of representation, we have a really good mixture of users from state bodies such as the Marine Institute and Enterprise Ireland, as well as Science Foundation Ireland, universities, and industry. So we're really pleased that we have been able to get this type of traction. It shows the interest in this type of work. So AWAMS stands for Advanced Water Monitoring System. This is a disruptive project that specifically addresses the global need, that specifically addresses the global need for lower cost, more accurate marine monitoring systems. Over the next 30 to 40 minutes, we will describe our project in detail to give you a thorough overview of the current state of development of AWAMS, which will be followed by questions and answers. Should you have any questions during the meeting, please use the chat functionality in Zoom, through which we will field questions at the end with our moderator, Professor Fiona Regan. Just a few housekeeping notes, which I see most of you already following. If you could just mute your microphones during the presentation, we'd be very grateful. And also just to let you know, this presentation is being recorded. So if you have colleagues who've missed this and who'd like to see it in the future, or if you have people of interest, it can be sent on at a later stage in time. So just showing you the agenda briefly, it's quite mixed between Dublin City University and ourselves, and I'm going to now kick it off. So my name is Charlotte O'Kelly. For those of you who don't know me, I'm the Managing Director here at TechWorks Marine. Why AWAMS? Well, as you're aware, there's an increasing need for marine monitoring internationally. This is being driven by an increase in population growth at an international level, with over 40% of the world's population living within 100 kilometers of the coast. It's also forecast that by 2050, over 70% of urban dwellers will be in megacities around our coastline. This puts increased pressure on the marine environment, notably the coastal one, which is where our focus is here on this project. It puts increased pressure in terms of food through aquaculture and feeding this growing population, clean water and sanitation, so desalination as well as wastewater, resource exploitation from oil and gas, but also marine renewables, transportation of goods in the global economy that we do live in. With this increased pressure on coastal waters, it is important to have cost-effective and scalable water monitoring equipment that can provide robust and reliable data, which can be transformed into valuable information to meet the challenges that the coastal users face. And here are just a few representations of, as we know, the challenges you face when you're managing activities and resources in the coastal zone. To put this into the economic context, it is forecast that the global market for environmental sensors will increase by 60% in the period of 2018 to 2023. This is partly due to the fact that marine monitoring is becoming a need to have rather than a nice to have, due to increases in regulations and also in industry and public awareness, and I'll come back to that in a second. This link with the transformation of the market from an expert user putting together bespoke systems, as is still common, is undergoing a transformation from an equipment-based to a data service sector, as can be seen in oil and gas and marine renewables. Underlying this is the need for high-resolution, quality-controlled data from which information products and services can be made available to the user community. So as we see, we've just been talking about the user community in terms of the expert user, the stakeholders, there's everyone here on this call, but there's also a new user which has always been around but is becoming in bigger focus now, and that's us as citizens. So our recreational activities and our leisure activities are also driving the need for much more information in the coastal zone. And this has been amplified in these COVID times that we live in, with much more people doing local recreational activities close by where they live and putting an increased pressure on the need for data in the coastal zone. So all this is why we have teamed up with Dublin City University and the Water Institute, led by Professor Fiona Regan, bringing in DCU's expertise in sensor development, as we will be showcasing in a few minutes, and TechWorks Marine's 20 years expertise at providing our clients with robust and reliable marine data. The AWAMS team seeks to address this through the transformative development of a high-resolution, multi-parameter optical sensor, which my colleagues in DCU are just going to go into in a second, and linking these sensors to the Coastline Mini Buoy and data analytics platform to provide a robust, high-resolution system to monitor coastal waters. As with any novel development, stakeholder engagement is critical to ensure that the sensor is measuring what the community requires. We have carried out this process last year at the start of the project to ensure we are focused on what industry needs. Today, the marine monitoring sector is fragmented between sensor manufacturers, integrators, and consultants who then process specific data for their clients. AWAMS is a water quality monitoring service directly to you as you need it. So before we go into the detail of the project, I'll give you a brief overview of our team. TechWorks Marine, we are an SME, a marine data SME based in Dublin. For our overseas guests today, Dunleary is a suburb of Dublin. We are being a bit precise there. Over the last 20 years, we have developed a multidisciplinary team of engineers, marine and data scientists, as well as Earth observation experts. We provide marine data services to a number of different sectors, notably ports and harbors, water, and coastal engineering. Core to our business, sorry, slide's not moving. Yeah. Core to our business is providing marine data as a service to our client. This makes our partnership with DCU a very good fit, as we are very complementary. And the fact we are located in the same city is a real advantage, even in the current COVID times, to ensure the successful delivery of AWAMS. I will now hand you over to my colleague Elena in DCU, who will introduce the team, the DCU team.
Good morning, my name is Elena Gomez Alvarez. The DCU team of the AWAMS project is a multidisciplinary team formed by analytical chemists, mechanical engineers, physicists, electronic engineers, biologists, and business experts. The project is led by Professor Fiona Regan. Dr. Cyprian Brichu is analytical chemistry that has greatly contributed to the sensor design. Sean Power is a mechatronic engineer who has played a crucial role in the sensor hardware and software development. Dr. Louis Free is a physicist and electronic engineer who is offering his expertise in optics. Adrián Delgado is a marine biologist who is developing anti-fouling strategies. Ruth Clinton is facilitating the industry collaboration and is also looking after the commercial aspects of the project. I am a PhD in analytical chemistry with more than 15 years experience in environmental monitoring. I joined the Water Institute in February this year, and I'm contributing my expertise in data analytics and sensor validation. There is a growing interest in marine and terrestrial observations involving satellite, aerial, and in situ sensing. This project arose as a consequence of the need to develop in situ monitoring solutions, including low-cost technologies for coastal areas. So the project framework consists of the following stages. First, it was sensor design. Then we moved on to building a first prototype unit. Then we will scale up to 10 units, integrate with TechWorks marine infrastructure, and finally, deployment and testing. Some of the challenges in coastal monitoring are biofouling, high capital costs, and high ownership costs of maintenance, spare parts, etc. To address these challenges and in line with the key performance indicators for design criteria, we have designed an optical sensor that uses three modes of transduction, absorption, scatter, and fluorescence. This would be the only detection technique that would successfully address all these KPIs. The goal is to develop a sensor that addresses challenges, including algal blooms, onset of flooding, and petroleum spills. The key performance indicators that have driven our sensor design are that it is robust and reliable, that it fully complies with marine specifications, that its design complies to a manufacturable specification, that is low cost and intelligent. So user needs led to the design of sensors to gather a first layer of data, parameters such as turbidity, chlorophyll A, and the rest shown on the left-hand side table, leading to a second layer of data which allow us to detect pollution events such as oil pollution, algal blooms, water discharges, or sedimentary suspension. So now I will hand you over to Cyprian that will describe Louis' work on the optical detection.
Good morning, everyone. Sorry for the delay. Thank you very much, Elena, and thank you all for joining us. My name is Cyprian. However, today I'm going to talk about Luis's input into the project and some of his work. So Luis, seen here in the picture, expertise in optical design, and to date he has been involved in designing and testing the optical head, and particularly in the optical head component selection process. For example, if you have an algal bloom, it's usually characterized by chlorophyll, and that can be quantified through fluorescence. The spectrum in the inset shows the output of the sensor using fluorescence detection, and oftentimes the optical band is selected for measuring and for measuring the concentration in water. The main drivers for the selection of the optical components are the environmental challenges, as Elena highlighted. And this work involves the selection of the LED sources, photodetectors, and optical lenses, and materials that provide the best trade-off between performance and cost. In our case, as a light source, the sensor uses an LED array spanning in the UV, visible, and infrared region of the spectrum, while for detector, it uses multispectral photodetectors, which are smartly integrated behind optical windows. Additionally, a lot of Luis's work was focused towards the selection of light coupling components. This includes collimation and focusing and optical alignment. This type of components require precise alignment and focusing to deliver sensitive selective detection, but also to limit the signal to noise ratio. In terms of testing, we've tested the sensor in a range of scenarios, including assessment of water quality through turbidity and chlorophyll, for example. This is the example for chlorophyll. So in the left, it shows the fluorescence spectra associated with the presence of chlorophyll at different concentrations, while on the right, you have an example of the quantification of chlorophyll through the calibration curve at an emission wavelength of 670 to 675 nanometers. Similarly, I have another example here for turbidity detection. Again, on the left, you can see the scatter data coming from the sensor at different NTU levels. And on the right, you can see the associated calibration curve at 850 nanometers. Overall, the performance of the sensor to date looks promising, and it is comparable with that of high performance off-the-shelf sensors, which enables us to move to the next stage and proceed with environmental testing and further sensor integration. This will be all from me, Louise, actually, and I will hand over now to Adrian, who's going to talk a bit about biofouling.
Hello, everyone. I'm Adrian. My role as a marine microbiologist working in this project is to test biofouling on the materials being used on the sensor. I'm aimed to develop methods and strategies to reduce biofouling that improve the lifetime of the sensor and above all, the quality of the data. Here's an example of the drift of an unprotected fluorometer due to biofouling, which caused the data lost, which is problematic. We have carried out several studies with different materials, copper and anti-fouling paints that are used in sensor design for 9 months to see their resistance and their effectiveness against the biofouling process. Here we can see a variety of fouling organisms as barnacles that established after several months on these materials. We are developing an anti-fouling system based on UVC radiation, which will prolong the life of the device and will reduce the maintenance cost. Now, I will hand you over to Sean, who will talk about design and engineering methods.
Thank you very much, Adrian. Hello, everyone. My name is Sean. My role as engineer on the project is to apply the engineering design manufacturing methods in both mechanical and electronics disciplines to develop and build the sensor prototypes. So this has involved a great deal of collaboration with our multidisciplinary team with inputs from chemists, biologists, physicists, and engineers. So onto the sensor design itself. On the left is a rendered CAD model with section view of the current design of the sensor we have developed, displaying some of the key features. The sensing materials and components were selected for their performance in the marine environment, from the connection cable, fittings, fasteners, and the enclosure, which are all rated for IP68 water tightness for full immersion over a prolonged period. The main properties we were looking for in the material selected were the robustness to stand up to the turbulent marine environment and chemical resistance to the saline coastal waters, with adherence to the international standards for marine environmental sensor performance. Different manufacturing techniques were used throughout this design. For instance, the housing is custom machined from a robust engineering polymer, acetal, and the optical head is fabricated from PETG using 3D printing technology. So for the electronics, the circuit boards were all designed and hand assembled in-house. The control board at the center is the brains of the sensor unit, and which carries out a number of functions to interact with the optical detection devices, take sample readings, process that data, and output it to TechWorks Marine's external network. So for this project, I used my background in mechatronic engineering to implement some engineering design methods. An iterative design process was used with input from team members at each stage of the sensor development. CAD models were produced to give visual representation through rendered images and dimension technical drawings for manufacture. The accumulation of the technical design and material selection was the fabrication of the physical sensor prototypes themselves. However, also the electronics provide the sensor's functionality. A full schematic of the control system was produced and ECAD software was used to design the circuit boards. Those designs were sent to a manufacturer and the boards were fabricated. A microcontroller on board is programmed to carry out the individual functions to operate the sensor and process the data produced by the optical detectors. So I'm now going to show a video documenting the assembly of the first prototypes produced in the Water Institute and tell you a bit about how they were put together. So we'll start off with the assembly line. So the components are laid out on the table there, everything from the electronic boards to the nuts and bolts. So the electronic boards themselves were fabricated by a manufacturer using the designs I produced, but they required assembly. So each component is hand placed and soldered using different techniques for the different components. Once assembled, they are tested and programmed. So now onto the 3D printing. So these are the optical heads being printed here. The components are printed from PETG, and each individual unit takes roughly 24 hours to print. Now, this is a time lapse of the internal frame being assembled. So this consists of 3D printed sections being connected by stainless steel rods, which then forms the mounting platform for the electronics and fits inside the sensor housing. So now onto the optical head assembly. So the individual sensing components are being put together, and then they are mounted on a tray structure, which fits snugly inside the optical head. So this allows for the sensors to be easily removed and also aligns the sensors behind the lenses once slotted in. So then the individual sensors are wired up and an output connector to the control board is seen there. The final steps are putting it all together, joining the optical head with the sensor housing, making sure everything is secure. And then the final steps is to mount the top cap, which we'll see shortly. So this top cap seals the sensor and provides external connections to TechWorks Marine's Mini Boy. So this is the finished sensor. We're ready to deploy this sensor now. So I'm going to hand you over to Glenn, who's the embedded system engineer for TechWorks Marine, to talk about the buoy systems and sensor integration.
Great, thanks very much, Sean. My name is Glenn Turpey, and I'm the embedded systems engineer here at TechWorks Marine. I've worked extensively over the past few years on the Mini Boy projects. If I can go here. You can see here, earlier this year, I visited the DCU Water Institute and got a tour of their labs, where I was handed over the instrument by Sean there, who looks great on the left there. So what is Mini Boy? Mini Boy is a kind of easily deployable data platform that's built for freshwater and coastal water environments, and it's generally suited to sheltered environments such as lakes, estuaries, ports, etc. It has 3 external sensor inputs. Each of those sensors can be multi-parameters, so you can have a variety of parameters all reported to the one data logger. It was originally developed for the EPA, and we've used it in multiple deployments, which my colleague Sinead will explain later on. It is a battery-powered system that can be rechargeable and deployed multiple times for multiple months at a time. You can see here on the right, the frame at the bottom was designed to protect the different instruments that can be attached to the frame to provide a level of protection. The floats were designed to be off the shelf, allowing us to very quickly reduce the lead time, which is very, very much a problem in the marine industry at the moment. Let's go to the next slide here. Once I received the AWAMS sensor from DCU, I began integrating the raw data from the AWAMS sensor into Mini Boy. That data is then packaged and transmitted via the 4G LTE or GSM network to AWS. It is transmitted via MQTT, which is a very popular IoT or Internet of Things telemetry system. AWS, or Amazon Web Services, is a cloud provider which provides a catalog of services, of which we use the IoT service. This is then easily packaged up and displayed on our data platform, CoastEye. One of the great advantages of AWAMS is it is an easily scalable solution. Using AWS, we can deploy multiple mini buoys in multiple locations for multiple deployments. This provides a very easily scalable and low power solution, and it provides real-time, high-resolution geospatial data to CoastEye. I will now hand over to Sinead, who will talk you through our trial deployments we've done over the last few years.
Thank you very much, Glenn. Good morning, everybody. So my name is Sinead McGlynn. I'm the Chief Operations Officer at TechWorks Marine, and I'm also the Consortium Project Manager for the AWAMS project. So as Glenn was saying, the Mini Boy is a very useful, very lightweight, easily deployable system. We've actually supplied the Environmental Protection Agency here in Ireland with the original version. So we developed the Mini Boy in association with the EPA due to their requirements for having something that was portable, lightweight, easy to deploy, and easy to recharge. So the eutrophication monitoring team in the EPA has been using the Mini Boy for the last couple of years for testing and for monitoring water quality. So in rivers, lakes and estuaries all around Ireland. You can see down here at the bottom left, you can get an idea of the actual size of the mini buoy once it's deployed in the water. So it's quite small and unobtrusive, and that was a big factor. The mini buoy can be deployed for up to about a month or so, powered by a battery. And there's also functionality to add solar panels to the buoy to keep it in the water for longer. But the battery is rechargeable overnight, so it's very straightforward to take the buoy out of the water, recharge and replace back in the water. It's also possible to have either a single or double point mooring on the buoy, depending on the location where you're putting it. So here we have an example from our coast-eye system of how the data is displayed on the mini buoy. So an example here of turbidity over a month-long period of time. So the combination of the AWAMS sensors plus the mini buoy plus our coast-eye system gives us an overall decision support system, which is what is being developed for the project. So this is the overall concept. The AWAMS sensors, which can be deployed either on buoys or on solid infrastructure, such as, for example, here the image on a bridge, are deployed at the location that the user desires. The data is then transmitted, as per Glenn's explanation, to a dedicated server where data processing and quality control is carried out. So this processing can also incorporate other data sources, other data from other sensors, data from models, data from publicly available data sets, or indeed data from satellites. This information is then collated and processed to give you the information required for the user. So taking the raw data and transforming it into meaningful information. We have identified that we have both non-expert and expert users who would be interested. So we would consider expert users being, for example, scientists, engineers, people working in public bodies who are being mandated to report on water quality throughout the island. Non-expert users, for example, would be citizens who are interested in water quality, whether they're out surfing, out sailing, out swimming. And as we all know at this stage, because we're not allowed to travel outside the country, we have a lot more people making use of the amenities around the coast. And so there's a much bigger focus in the past year or so on the conditions within Ireland as to how you can actually enjoy the amenities. So the expert users can access the decision support system through our coast-eye platform. They can access the information from the sensors. They can access reports. They can download statistics. They can evaluate historical trends, so the historical data sets, but also be informed or be alerted when unexpected events happen. So for example, if there is an algal bloom or if there's oil detected in the water where the sensors are deployed, people can be notified via alert of when you have an excess. Non-expert users, so citizens, can also access the decision support system, whether it be through a laptop or through your mobile phone, and can request alerts for custom locations or for custom times, and also request alerts for high-risk conditions. So where you have an incident around pollution or algal blooms, they can be notified when it is or isn't safe to enjoy the water. So the system is built on our coast-eye platform, which is TechWorks Marine's operational system. So this is proven technology that we have been using in-house operationally for the past 15 years. The system is composed of different modules. So you have a system to integrate and store both in situ data, so from the AWAMS sensor, for example, and provide time series. It also has functionality to integrate other sources of data. So for example, satellite data, other types of geospatial data, and model data, publicly available data. And then a web application, the front end, which provides the users with the access to the information. This can all be tailored to the specific user and is available through secure access. The idea here for the decision support system is that you can have both multiple data sets coming from single platforms and also a large distribution of platforms providing you with similar information. So here, for example, on the left-hand side, we have a number of buoys deployed in Dublin Bay. The buoys have sensors mounted on them at different levels, so you can measure the parameters at different levels, but you also can compare and cross-validate against each other. So this is giving multiple sensors, providing multiple types of information from single platforms. So here, for example, we have wave data and turbidity data being produced on a long-term basis. The fact that you have multiple data sets available from single platforms allows you to cross-validate data. So you can use, for example, other sensors which are high performance and used as recognized standards across the world and validate the AWAMS sensor against these. This gives people the kind of confidence and the security that what the information that they're being given is accurate. It's also possible, as Len mentioned there, with the mini-buoy network, to have a large network of sensors which are all measuring the same thing. So you can have multiple sensors, multiple deployments covering a large area, giving you different types, or giving you the same information at different locations. This can also be overlaid by satellite data, which can give you even larger scale data sets and allow you to really have a very large area as an input to the decision support system. So the next steps in the project are to validate and verify the operations of the sensors against these high performance sensors, and then also to carry out a number of use cases over the next year and a half to verify and validate the sensors and to verify and validate the information for users. So if you're interested, please contact us afterwards. I'm now going to hand back to Charlotte to talk about the disruptive elements of what we're doing within this project.
Thank you, Sinead. So I hope you have found this overview of our project quite interesting. We have given you a snapshot tour of a significant amount of work. So there's a lot of detail that has not been gone into in this presentation. But should you have any questions, please use the chat functionality. I see there's questions that have been coming up during the presentations, but also feel free to contact us, either Sinead or Ruth, or myself, and all the details will be there later. The important thing with AWAMS is really the disruption that it's going to be bringing to the system. We've been talking about it throughout the presentation, but the disruption is that we know there is a need for increased monitoring. Monitoring at the moment, the main barrier to it is access to technologies, either due to price or due to data accuracy. And these are all being catered for in AWAMS. So in AWAMS, we are specifically looking at cost reduction. This slide below just shows that on the platforms, that the mini-buoy platform can basically house the same amount of sensor packages as a much larger platform at a much lesser cost. So we're driving down the cost of marine monitoring, and this is one of the main barriers to access to the sector for mass monitoring. We are also making it a lot easier to use. It's about providing users, be they me, the citizen, or me, the expert, with information products that I can then use to manage my operations. And I saw we had a comment about streams and estuaries on the chat. It's about that. It's about making the data accessible as information for the user communities and the citizen scientists. You know, the easy to use is the data, but it's also being able to rapidly respond to events as they happen, to be able to literally pick up the AWAMS sensors in the mini buoy, put them in the boot of the car, take them to a small boat, easily deploy them, come back 3 months later, having received the data you require as and when you require it during that intervening period. That's really the big change. Not having to worry about large boats, large budgets, large through life costs, but being able to react quickly as and when issues happen. So in closing, what we really are looking at is transforming marine monitoring at a global level, being able to have networks of low-cost IoT platforms which send data directly through to users, directly through Amazon Web Services in a seamless way, so that we have a better understanding of the coastal zone, irrespective of our use, because everyone has a slightly different use of the data. So, you know, hopefully this has given you a really good insight into what we're doing. Again, Professor Fiona Regan is going to be the MC for the Q&A session. She's now come on live on screen there. And we really want to be engaging and engaged with the stakeholder community. That has been a core part of this work since the get-go. And so as part of, you know, our webinar today, it's about engaging with you, thanking you for taking the time to listen to us and to hear about our exciting developments, but also come to us and talk to us about how we can work with you, collaborate with you about, you know, with the AWAMS solution. Okay, on that note, I'll hand you over to Fiona. Thank you very much, everyone.